Hi, this is Babak. In this video, I'm going to solve the following problem for you. This is a problem in linear algebra on the topic of systems of linear equations. Let me read the question for you first. Consider the following system of equations in x, y, and z. Kx plus ky plus z is equal to 3, 2 times x plus k times y plus z is equal to 2, and 4x plus 3y plus 3z is equal to 8. Number 1. For which value of k does the system have a unique solution, no solutions, or infinitely many solutions? Number 2. Solve the system for k equal to 1. This problem has been chosen from an exam question on the course Linear Algebra and Geometry with the code number SF1624 at Royal Institute of Technology, KTH, Stockholm, Sweden. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. If you do everything correctly, the answer that you will get at the end is this. The system is consistent if and only if k is equal to 2. It has a unique solution if and only if k is neither equal to 1 nor equal to 2. And it has infinitely many solutions if and only if k is equal to 1. And one possible form of the set of solutions in that case would be this set that I have written here. Okay, now let us start solving the problem. I want to use Gauss elimination method first to solve this problem. But of course, if I start as usual to construct the augmented matrix corresponding to this system, usually we start with k variables first, so we write k, 2, and 4, and then y variables, and then z variables, and then finally we have 3, 2, and 8. Yes? But of course, it's completely okay if you want to do this, but if you give it a try yourself in this way, the calculations become very tedious. And the reason that the calculations are becoming very tedious, because none of these entries on the first column is equal to 1. So it means that you need to work with fractions and all the time need to be worried about if you are considering all possibilities for making sure that you are not dividing by a 0, which is not very apparent sometimes. Okay, I would change my strategy to tackle the problem in the first place. Okay, I see that the z variable, there are two positions that z variable appears with a coefficient equal to 1. So this motivates me, first of all, change the form that this equation appears actually. So I would say that, okay, my goal is to solve this equation, kx plus ky plus z equals to 3, and 2x plus ky plus z is equal to 2, and 4x plus 3y plus 3z is equal to 8. Of course, no one prevents me to write this equation in a more appropriate and equivalent way. Namely, I would write it in this form: z plus ky n plus 2x equals to 2. Yes, so what you see here is exactly this equation that I have here, z, and then I have ky, and then I have 2x. The reason that I want to do this, because I want to have this coefficient equal to 1, makes the calculation simpler. Okay, so, and then I go to the next one. I would write it as z plus ky plus kx is equal to 3, and then finally I write the other equation. So actually I am changing the columns in principle. Yes, plus 4x is equal to 8. So what I have done, I have essentially written the same system, But what I have done, I have taken this one and put it in the first equation by changing this one and this one as well. But nobody doubts actually this is exactly the same equation here. And then I have z plus ky plus kx equal to 3, which is exactly this equation, and this equation is exactly this one. So it's completely clear that this system is exactly the same system. But what is the good point about that? Because now if I start writing the augmented matrix, then it becomes 1, k, 2, and 2, and the other one becomes 1, k, k, and 3, and then I have 3, 3, 4, 8. But something that you need to be careful about is that this now, the first column is not the x column, is the z column, and the second column is the y column, and the last one is the x column. So you need to be careful about this order until the end of this problem. Now I will start using Gauss elimination very easily. Yes, namely, I will copy and paste the first row. Yes, so it is 1, k, 2, 2, but I multiply the first row by a negative sign. It becomes minus 1 minus k minus 2 minus 2, and then I will add this to the second row. And I will multiply this next time by a negative 3, and what I get here and here and here, I will add them to the third row. Okay, so let us do this in one go. This becomes 0, and then this also becomes 0, and then this becomes k minus 2, and then I will have 1 here. But here I will have 0, here I will have 3 minus 3k, and then here I will have minus 2, and I will have 2 here. Yes? Okay, sorry. So what I now understand is that I need to interchange this row with that row, then I am done. As simple as that. So I have my matrix in row echelon form. 1, k, 2, 2, 0, 3 minus 3k minus 2 and 2, 0, 0, k minus 2 and 1. Okay? So my point is that it's also a nice trick. If I wanted to start from the augmented matrix of the system in its original form, of course it is doable, but because these numbers are not 1, even if you interchange these two, then you will have a 2 there. So you need to start working with a little bit odd numbers. But of course at the end, if you manage that, that would be quite equivalent. But you see, in 2 steps actually I am done. So remember this trick of changing the columns sometimes if necessary, or sometimes if you can solve your problem easier. Okay, now let us discuss about the problem. First of all, check inconsistencies. When this system can be inconsistent. This system can be inconsistent if I have facing such a row so that everywhere is 0 except the last one. Okay? So when this can happen, this cannot happen of course in this row because I have non-zero numbers here. So the only possibility that this might happen is the last row. So what does it mean? It means that I want, for inconsistency, I would say that the system is inconsistent if and only if k minus 2 is equal to 0, or equivalently k is equal to 2. And that is exactly what is given in the answer. Because if k is equal to 2, then I will have 0, 0 here, and then I will have 1. This kind of rows is forbidden, so it is inconsistent. Now, assume that the system is consistent. So now, let k be not equal to 2. Every discussion is coming now is based on this fact that k is not equal to 2, because if k is equal to 2, the system is inconsistent. So k is not equal to 2, I want to go for a unique solution. So for a unique solution, in the coefficient matrix here, the number of pivots should match the number of variables. But you know that I have only 3 variables. Yes, so it means that for having a unique solution, I have to have exactly 3 pivots. Of course, this consideration is done under this condition, so good, I have 1 pivot here because this condition guarantees that this is non-zero. So this is 1 pivot, and I know that 1 is not equal 0, so it is the second pivot. For having the third pivot, it means that this shouldn't be equal to 0, okay? So the number of variables, let me write the number of unknowns is equal to 3, and the number of, so this, the number of pivots, if I want to make it equal to 3, so let me write it in this way. So in order, but let me write it in this way. The system has a unique solution if and only if the number of pivots is equal to the number of variables or the unknowns, and that is equal to 3. So this happens if and only if k is not equal to 2, because I am solving this under this consideration, and on top of that, and 3 minus 3k is not equal to 0. So this means that this is actually equivalent to saying that k is not equal to 1 and k is not equal to 2. Yes? So this is for having a unique solution. But for having infinitely many solutions, the number of pivots should be smaller than the number of unknowns. So the number of unknowns is of course 3, and of course I am solving it under this condition, so it means that this is a pivot, definitely this is a pivot because this is not 0. But I want to have less number of pivots than the number of variables. If the last one is a real pivot, then what will happen is that I will have 3 pivots, which gives me a unique solution. So it means that here the system has infinitely many solutions if and only if k is of course not equal to 2. You don't need to write it all the time, but and then 3 minus 3k is equal to 0. Okay? And so this means that k is equal to 1. And then you realize you don't need to emphasize here, because when you say that k is equal to 1, automatically you are also considering this condition. This was not the case for having a unique solution. If you just write this one is not equal to 1 and don't write that, that would be wrong. Okay? So here, but when you say that k is equal to 1, it automatically means k is not equal to 2, so you don't need to emphasize it again. So I would say that, okay, the system has this if and only if that k is equal to 1. So if you go back and compare now, so we realize that the system is inconsistent if and only if k is equal to 2. The system has a unique solution if and only if k is neither equal to 1 nor equal to 2, and it has infinitely many solutions if k is equal to 1. Now I want to solve that for the latter case when k is equal to 1. Of course I can put k equal to 1 and start everything from scratch, but I don't need to do that. I just put k equal to 1 here. So for this purpose, let me just take this with me to the next page so that I have enough space to write. So I will take it with me and I will go here. Okay, now let me paste it here. And now I have k equal to 1 and I want to solve that. But remember, let me emphasize again, so let me paste it here, a little bit of space. So if you remember, let us go back now here. What you see, these are the orders that I have chosen, z, y, and x. So let me just write here on top so that I don't forget about it. So z and y and x. Okay, now k is equal to 1. So k is equal to 1, implies that I have this row echelon matrix. So there was an entry missing here. Actually, I don't know what happened by this copy and pasting. So there are zeros here. I don't know what happened. So let me do it once more. So yes, I probably didn't copy everything. Now that's good. So let me go back here, clean everything, and paste it once more here. Yeah, I think it's correct now. And then let me write the order here as well. So this was z, y, and x. Okay, sorry. And then I have k equal to 1. So then what happens? I will have 1, 1, 2, and 2, 0. If I put k equal to 1 there, it also becomes 0. I have minus 2, 2, 0, 0, minus 1, and 1. Of course, now let us make it into a row echelon form here finally, because I can just divide the second row by minus 2. It becomes 1, 1, 2, and 2, 0, 0, 1, and minus 1, 0, 0, minus 1, and 1. And then what happens is that I add the second row to the third row. So as we predicted, actually there are 2 pivots only, so this means that definitely my system has infinitely many solutions, because I have 3 variables, then I have only 2 pivots. But this column is a pivot column, yes? This column is a pivot column. This column is also a pivot column. Yes, because my pivots are actually, this number here is a pivot, and this number is also here a pivot. So these are 2 pivots. So it means that the z column and the x column contain pivots, but the y column does not contain any pivots. So it means that is a free variable. Yes. So I would say that y is any number like t. Then I would do back substitution method to solve the problem. It means that I will rewrite my system again using this reduced echelon form of the augmented matrix. But again, careful. The first one is z, the second one is y, the last one is x. There is nothing to write for the last row except writing 0 is equal to 0. So I will start from here. What should I do? I would write 0x, 0, 0 times z plus 0 times y plus 1 times x is equal to minus 1. So definitely x becomes equal to minus 1 is my answer. Okay, and then I go to the above row, so it becomes 1 times z plus 1 times y plus 2 times x is equal to 2. Okay, and then of course I also know that y is equal to t, my free variable. So then I can put them in the first equation. Then I will have z plus t, and then I will have minus 2 is equal to 2. And then what happens is that z is equal to 4 minus t, and that is my z that I was looking for. So if I want to write the solution set, one way of writing that is of course to write minus 1 t and 4 minus t, where t is a real number. Okay? So the whole point of this problem, from my point of view, is the trick, a little trick, that changing the columns will not, of course, change the solution set, but it will facilitate sometimes and save a lot of time for us. Okay. One other way to look at this problem that's also good to see, and that is the notion of determinant. Especially, the determinants are good when we want to talk about the unique solutions, because we know that the system of this kind, in which the number of equations is equal to the number of variables, has a unique solution if and only if the determinant of the coefficient matrix is not equal to 0. And because calculating 3 by 3 determinants are very easy, so that's also an option here. So let me write second method, okay? So second method. Okay, so how should I do this? I will calculate the determinant and say that the determinant should not be equal to 0. So the determinant is not equal to 0 if and only if the system has a unique solution. So, or it's better to write it the other way around. So I would say the system has a unique solution if and only if the determinant of the coefficients, so here you don't need to change anything at all. So you just write k with the original system, you can immediately start. And 2, k, and 1, 4, 3, and 3. This shouldn't be equal to 0. Okay? And then what you do, you just expand the determinant. And this is if and only if. Let me just expand the determinant so it becomes k. And then I have a 2 by 2 determinant here, and then I will have minus k, then I will have a 2 by 2 determinant here, and finally I will have 1, 2, k, 4, and 3. This shouldn't be equal to 0. So what I have done, I have taken this one, and I eliminated these two, so I will have this 2 by 2 determinant here. When I go to the middle one, I have to put a negative sign, and then I will eliminate these two, so 2, 1, 4, and 3. And then finally, I will go here 2k, 4, and 3. Now let me just expand that. So this is if and only if k times 3k minus 3 minus k. So the determinant here is 6 minus 4 is just, let me just write 6 minus 4. And then the other one is 1, 6 minus 4k. This shouldn't be equal to 0. And then let me just simplify. So this becomes 3k squared minus 3k minus 2k. And then I have positive 6 minus 4k shouldn't be equal to 0. And after simplification, I will have 3k squared minus 9k, and then finally plus 6. It shouldn't be equal to 0. If I divide by 3, it becomes this. Of course, you can use ABC formula to solve that, but I think it's easy to factorize here, so it becomes k minus 1, k minus 2, sorry. It's not equal to 0. It's easy to check. If you multiply this, you will get this. And then if this is not going to be 0, this happens under this condition that neither of one of these factors is equal to 0. So this means that k shouldn't be equal to 1 and k shouldn't be equal to 2. So that's exactly what we found using Gauss elimination method. So the system has a unique solution if and only if k is not equal to 1 and k is not equal to 2. Okay, then what we can do, what happens for this, so one part of the problem is actually finished, but now you realize that, so I would say something like this. I would say unique solution, so let me just write it in a summarized form. So unique if and only if k is not equal to 1 and k is not equal to 2. Okay, so this, what does this mean? It means that not unique is equivalent to not this. Yes, so not this means either k is equal to 1 or k is equal to 2. But not unique in in the linear systems, you know, it means two scenarios. It means either inconsistent or infinitely many. Okay, so you see the trick was to find out when the system has a unique solution using the notion of determinant. When this is settled down, it means that not unique should be the negation of this statement, which would be this one. On the other hand, in the theory of linear systems, not unique means either inconsistent or infinitely many solutions. So it means that then this becomes equivalent to saying that k is equal to 1 or k is equal to 2. But of course we don't know which one is which. Might be both of them gives rise to inconsistent system, or one of them gives rise to inconsistent system and the other one gives rise to an infinitely many solution system with infinitely many solutions. We need to discover this. But then it is easy, because at least you don't need to work with an augmented matrix that contains a variable in it. Because if the augmented matrix contains any variable, then it would be problematic sometimes, because the algebra becomes a little bit more involved. But it means that now I know that I have two scenarios to think about. K is equal to 1 or k is equal to 2. And then of course I can put k equal to 1 and solve a system with k equal to 1. There are no parameters involved. And then I can put k equal to 2 and solve the problem again to see which one is inconsistent one and which one gives rise to inconsistency and which one gives rise to infinitely many solutions. Okay, so for example, if I put k equal to 1, then what happens? It becomes x plus y plus z equals to 3. And then the second equation would be 2x plus y plus z is equal to 2. And the last equation would be 4x plus 3y plus 3z is equal to 8. So, but you see that there are no parameters involved. So what I can do, I can immediately use the Gaussian elimination to understand what's going on. So for example, here I can write 1, 1, 1, 3. So my point is that I don't need to work with an augmented matrix containing parameters, which is hard sometimes. 4, 3, and 3, and 8. So for example, I can just copy and paste the first one and multiply the second 2 times that one, so it becomes -1, -1, and -4, and then multiply -4 here, -1, -1, and -4. Okay, so immediately it becomes clear. You see, no messy calculations at all. So I do it once more. So what I do, I multiply the second row by a minus sign and add it to the last one, becomes 0, 0, 0. So then of course you immediately see that you have 2 pivots, so this means that this is infinitely many solutions. So infinitely many if and only if k is equal to 1. And of course then you can repeat. I don't want to repeat. You can just use this to solve your equation again. So that is left as an exercise. So you can use now this augmented matrix to solve that system. Okay, and then what happens for k equal to 2? So k equal to 2, if I put 2 here in this equation, then I will have this system 2x plus 2k plus z equals to 3. Then I have 2x plus 2, sorry, this was not 2k, this was 2y, again 2y plus z is equal to 2. And actually you see that you really don't need even to solve anything here in this problem, because it's clearly inconsistent, yes? Because the first equation is telling you that this combination is supposed to be 3, and simultaneously the same combination has to be equal to 2. So it means that this is inconsistent. If and only if k is equal to 2. And then you see that you exactly got the same answers, yes? A unique solution, neither k should be equal to 1 nor 2. K equal to 1 is infinitely many solutions, and k is equal to 2 has no solutions at all. Yes, so of course if you want to, you can let us also solve this equation. For example, if I want to solve that equation when k is equal to 1, I need to solve this. So here I haven't changed anything. So this is still the x row, this is the x column, the y column, and the z column. And then here this is one of my pivots, and here this is also another pivot that I have. So then it means that the z column is without any pivots. So if I want to solve that system, what happens is that I have to put z equal to a free parameter, yes, and then I should write my equation. So the equation would be minus y minus z is equal to minus t, and the first equation is x plus y plus z equals to 3. Hopefully I haven't done any mistakes. And then I put a t here, so this means that y is equal to 4 minus t, yes. And then if I put that in the first equation, I don't know x, but y is 4 minus t, and z is t, and then 3, so definitely x becomes negative 1. Again, x, y, and z is minus 1, 4 minus t, and t. And that's exactly the same answer. Even if I want to discuss a little bit more about this problem, an alternative way of solving this problem would be this. Okay, so let me take this one with me so that we can have it in front of our eyes. So another one that we can do here is eliminate one of these variables as if that you are doing it very elementary, because 3 equations in 3 unknowns is not a big deal. So for example, what I do, I will choose the best one. From my opinion, the best one is this one, and I want to find z from this equation. So then this z becomes 2 minus 2x plus ky. Then I plug it into the first equation, so it becomes kx plus ky. Instead of z, I plug this expression in. Oh, I made a mistake. So this is negative sign. So this is also a negative sign. And then what happens here is that I have this one equal to 3. And then this ky and this ky are gone. So I am left with k minus 2x, and then is equal to 1. This is one equation. I put it in the third equation. I multiply it by 3. 6 minus 6x minus 3ky is equal to 8. Let us simplify this a little bit. So this becomes minus 2x, and then I will have plus 3 minus 3ky, and on the right hand side I will have 2. Now the strategy is that let us concentrate on this system of 2 equations in 2 unknowns, but you need to understand the reason behind that. Assume that there are infinitely many answers for this system. You take any pair from these infinitely manys and put them here. You also get some value for z. So it means that if this system has infinitely many solutions, your original system also has infinitely many solutions. If you cannot find any x and y from this, it means that if this system is inconsistent, your original system has to be inconsistent, because if your original system has a solution, the xy part of that solution should be a solution to this. Okay? And then assume that you have a unique solution coming out from here. One for x, one for y. If you just take those values for x and y and put them here, you get a unique value for z. So having a unique solution here gives rise to a unique solution to the original equation. So actually they are equivalent. So now it means that instead of thinking and doing Gauss elimination for that 3 by 3 matrix, I can just concentrate here. And again, if you don't mind, let me use the trick again. So let me write the y variable first. So then the augmented matrix for this would be 3 minus 3k and minus 2 and then 2. Here would be 0. The reason that I chose it here, because this would be already in row echelon form. Yes? What I am doing, I am just rewriting this in this form, which is the same equation essentially. and then I am putting it here, so then it becomes yeah, I'm writing this one also as the first one, the first row, and then I go here, I have 0, the x component is k minus 2, and then I will have 0. So you see that this was easier to do because this is already in row echelon 4. And then I will have the same scenario. So when this system has infinitely many, when this system is inconsistent, the system is inconsistent when k is equal to 2, because then I will have 0, 0 and a non-zero number here. So you see that I get k for inconsistent. Okay, now assume that k is not equal to 2. If k is not equal to 2, then it means that definitely I have one pivot here. Okay, and that one pivot, if this is also another pivot, then I will have two pivots and two variables in my equation. So this means that I will have a unique solution. So it means that if I have, so if 3 minus 3k is not 0 on top of this condition, meaning that k is not equal to 1, I have a unique solution. So unique is if and only if k is not equal to 1 and k is not equal to 2. But now that I am sure that k is not equal to 2, so definitely I have one pivot here. But if I want to have infinitely many solutions, I need to have exactly one pivot, not more than that. Yes. So this means that this 3 minus 3k should be equal to 0. So this means that k should be equal to 1. Okay? And of course, if k is equal to 1, what will happen here? Then you will get 0 minus 2, 2, 0 minus 1, and 1. So what I can do, I can, for example, divide this by negative 2, it becomes 1 and minus 1, 0 minus 1 and 1, and then add it to the next one, it becomes 0, 1 and minus 1, 0, 0, 0, and then just do the backward calculation to simplify that. But remember, this one is the y column, this one is the x column, and the pivot appears on the x column. So it means that y is not a pivot. So y is my free variable again. So what I can do, I can write y is equal to t, and then I write this system, the last row of course is 0 equal to 0, but the first one is x equal to minus 1 again. You see, I'm getting the same answers over and over again, and then you can just block them back to find the solution. So I was thinking that in this video, if I collect all these possibilities for solving this problem, that would be useful for you. I hope that you also found the video helpful. I will put the PDF to the I will put the link to the PDF file of these notes below this video. Okay, and then you can download it and read it instead of actually watching the video. Okay, until the next video, be safe and goodbye.